The binary multiplication between two unsigned integers works in a way analogous to the manual process used for decimal multiplication, which is based on the summation of partial products. The product of two binary numbers of n bits and k bits is a binary number of n plus k bits. Each partial product is obtained by multiplying the bit of the multiplier with the multiplicand. In simple terms, if the multiplier bit is 1, then the partial product is composed of the multiplicand shifted left by as many positions as the position of the multiplier bit that generated it. If instead the multiplier bit is 0, then the partial product is clearly 0. Below we see the example of the multiplication between the unsigned binary numbers 1101, that is 13, and 1011, that is 11. The matrix of partial products is constructed by placing the multiplicand appropriately shifted on the first, second, and fourth row, while the third row is 0. The column-wise summation of the partial product matrix produces a result equal to 10001111, that is 143. As expected, the solution is represented on 4 plus 4 bits, hence 8 bits. By looking more closely at the matrix of partial products, we can observe that each of the 16 terms is nothing more than the arithmetic product of 2 bits, one from the multiplicand and one from the multiplier. From an implementation perspective, every partial product can be easily obtained through an AND gate that takes in input those 2 bits. For the case of 4-bit operands, the two figures shown in the slide illustrate, on the left, the logical diagram of the partial product matrix, and on the right, its equivalent circuit diagram. The generation of the partial product matrix is only the first phase of the multiplication algorithm, and it is identical across all types of multipliers described in the literature. What differentiates the various multiplier architectures is the mechanism used to sum the partial products in order to obtain the final result. We can notice that, in order to generate the solution of the multiplication operation, it is necessary to add together all the rows of the partial product matrix. To accomplish this for two n-bit operands, we would need a specific combinational circuit capable of taking as input n-squared variables, that is, all the partial products, and producing 2n output values. Designing such a circuit using custom techniques would require a new design for every value of n. As an alternative, the literature presents multiplier architectures with a regular structure that scales with the value of n. Some of these architectures will be shown in this video, and in particular, the multiplier with row-wise addition, the multiplier with diagonal-wise addition, and the multiplier with column-wise addition. All these architectures, despite being based on regular structures, differ in the way carry signals are propagated. In fact, as with adders, the carry chains are what determine the performance of the arithmetic unit. Let us begin with the so-called row-wise multiplier. This multiplier is an architecture that, from a logical perspective, performs the additions row by row. The logical view is shown in the small image on the left, where each red rectangle represents an n-bit adder. This multiplier uses n-1 adders. First, it adds the first 2 rows of the partial product matrix, then it adds the obtained result to the next row, and continues in the same way for all the remaining rows. The main diagram in the slide shows in detail the grid of full adders in this architecture. Some of them, highlighted in yellow, have only 2 inputs and can therefore be implemented as half adders. The diagram also illustrates the data flow, composed of the adder outputs and carry signals propagated through the components according to the scheme discussed earlier. As a final remark, we can observe that the regularity of the multiplier structure is clearly visible. Let us now briefly focus on the evaluation of the adder latency. The latency of an adder architecture can be measured in terms of the number of full adders or half adders that must be traversed to produce all the bits of the result. In this case, the orange arrow identifies the critical input to output path, which spans 8 full adders or half adders. In general, if the adder operates on n-bit operands, the latency is 3n-4 full adders or half adders. The second architecture we examine is the diagonal-wise multiplier. From a logical point of view, it performs additions along the diagonals. In practice, instead of summing the terms of the partial products within the same row, the adders progressively shift to the next rows. The logical view is shown in the small image on the left, where each red rectangle represents an n-bit adder. This architecture uses n adders, each n-1 bit wise. n-1 adders are used to perform the diagonal sums. The remaining adder, depicted orthogonally with respect to the previous ones, collects the outputs of the last bit of the former n-1 adders, both the sum result and the carry, and finalizes the multiplication output. As in the previous case, the main schematic in this slide illustrates in detail the grid of full adders and half adders included in the architecture, once again highlighting the regularity of the structure. Here we can clearly observe how the carries are propagated diagonally, following the direction of the adder chain in the logical diagram. Although the number of full adders and half adders is the same as in the row-wise multiplier, the difference between the two implementations becomes evident when we look at latency. The critical path, highlighted by the orange arrow, propagates diagonally, and only in the final stage does it proceed horizontally through the last adder. In this specific example of a 4-bit multiplier, the latency is 6 units, and in general it can be expressed as 2n-2. The last architecture we examine adopts a method similar to the one used when performing decimal multiplication by hand. In this case, the addition is carried out column by column. Thus, the addition now involves summing all the bits required to generate a specific output bit of the result. Summing many bits is equivalent to counting how many of them have the value 1. This counting operation is performed by the so-called parallel counters. For each column, the parallel counter takes in input the partial product bits present in each column, together with any carries coming from the sums of the previous columns. The figure at the top right of this slide shows the logical structure of the column-wise multiplier. The counting performed at each stage produces the output bit associated with that column, as well as any carries that must be propagated to the next stages. The figure at the bottom right shows an example of a parallel counter for a 5-bit input. Since the greatest number it can produce is 5, that is 101 in binary representation, it outputs 1 result bit and 2 carry bits to be propagated to the counters on its left. This figure also highlights a graphical convention commonly used for parallel counters. The counter block does not display its inputs explicitly. Instead, the input bits are implicitly represented by the dots enclosed within the rounded outer rectangle. Let us look at the example of a 6-bit column-wise multiplier, starting by building the matrix of partial products. Each black dot represents one of the partial products in the matrix. We now build, on top of the partial product matrix, the column-wise multiplier, showing the counters as rectangles. We can observe that the size of the counters extends beyond the pure matrix of partial products, because each column must also take into account the carries arriving from the previous columns. In the figure, these carries are shown as red dots. We now remove the green trapezoid to make the generation of the carry signals of each parallel counter clearer. The red arrows are used to indicate the origin of each carry in the figure. We can also observe that the last carry out is discarded, since it extends beyond the 2n bit width, 12 bits in this case, required to generate the correct result. If we focus on the latency of the multiplier, we notice that its value is determined mainly by the carry chain formed across the various columns. In practice, the arrow highlights the critical path that traverses all the counters, resulting in a latency equal to 2n-1 counters, 11 in this case. In the current configuration, the latency is actually worse than in the previous architecture. However, this method opens up several opportunities for optimization. For example, the possibility of postponing the carry counting to a later stage. To avoid the propagation of carries, the idea behind the alternative version of the column-wise multiplier is precisely to postpone their use to a later phase. This alternative scheme, shown in the figure on the right, breaks the column summation process into 3 stages. The first stage performs the column-wise summation of the partial product matrix only. The second stage uses parallel counters to reduce the number of terms in each column down to only 2. This phase may consist of multiple intermediate reduction steps. The third and final stage uses a fast adder to compute the remaining columns of the product. The advantages of this method are related to its speed. The delay is dominated by the final adder, which can be implemented using a fast addition architecture. However, this architecture also shows a major drawback. The regularity of the structure is lost because each column requires different counters with variable input sizes, potentially large in number. To solve the problem of variable size counters, two well-known implementations were proposed by Wallace and Dada, both relying exclusively on counters with 2 or 3 inputs, corresponding respectively to half adders and full adders. Without going too deeply into the details of the two implementations just introduced, we can look at how they are structured for a 6-bit multiplier. The Wallace multiplier implementation shown on the left replaces the n input counters with counters that have only 2 or 3 inputs, namely half adders and full adders. It requires a few more intermediate stages, but in return, it provides improved regularity and smaller counter sizes. On the right, we can see the implementation of the Dada multiplier, which improves upon the Wallace solution in terms of the number of counters used. The key insight introduced by Dada is to perform counting only when necessary, that is, to use counters only when avoiding them would result in increased latency, and thus additional stages of the multiplier. As a brief side note, since you are attending the bachelor's degree in computer engineering at the Politecnico di Milano, I would like to mention that Professor Dada was both a faculty member and a rector of our university, and he was the one who brought the first functioning computer to Italy and to continental Europe, which is still visible today in the entrance hall of the Department of Electronics, Information, and Bioengineering.